Right. So, yeah, I think in our last class we have seen about resonance in LCR circuits, right? Resonance and resonance in series LCR and resonance in parallel LCR circuits, right? So, hope you must be able to solve any electronic circuits or any AC circuits for their resonance frequencies. I will upload a tutorial, right? Once all the sections are completed, I will upload a tutorial so you can practice it, right? For both resonance frequencies and all, right? Okay, now we'll see about the transient response of inductors and capacitors, right? Transient in capacitors and inductors, right? So first we'll see about transient in capacitor, right? Transient in capacitor. As you know, earlier we have seen that the current through a capacitor can be simply written as I equals C into D dt of V. Am I right? Where V is the voltage across the capacitor. So when V is constant or DC voltage, right? In other words, if V is DC, then dt of V will be 0, right? Hence, I will have current which is equal to 0, right? So this current is actually the steady state current. Right? Steady state current, right? But when you connect a capacitor across a DC voltage, there will be a transient current, which means at the beginning, right, there will be no charges stored in the capacitor, and during the charging of capacitor, there will be a current, right? And that is called as the transient response or transient current, right? We'll see how a capacitor, right, or behaves when it is connected with a voltage, right, or a current across it, right? So now consider circuit, right? Okay, with the battery, right? So that's a switch, plus or minus, right? This is a switch. Then we'll have resistance R and the capacitor C is connected here, right? C, right? This is C, right? So there will be a current here, and that will be a function of time, right? So let me write it as I of t, right? Can you hear me? Sorry, this is not switch. This is actually V. This will be switch, right? Can you hear me, guys?
Yes, sir.
Is the figures and writing clear to you?
Yes, sir.
Okay, okay, right. Right, so R and C. So once the switch is closed, there will be a current, right? There will be a current, and that will be a function of T. So we can write it as I of T. Or I would say the current is a function of time, right? Function of time. So say when t equals t seconds, right? At t equals t seconds, assume that the current I will be equals I of t, and the voltage across the capacitor, the voltage developed across the capacitor, right, will be Vc of t, right? Vc of t, right? Just assume that now I close the switch and I am applying Kirchhoff's current law. So I can write that I have only one voltage source, which will be V, and then that is equal to I of t into R, and then, yeah, the voltage across the capacitor. So I can write it as R into I of t plus the voltage across the capacitor, which is Vc of t, right? Vc of t. And also we know that the current I of t can be written as d dt of q of t, right? The charge d dt of q of t. Right now, just combine these two together, right? These two together. So I can directly write it as, yes, of course, from this equation, just cross multiply this one, right? So I would say dq of t can be written as, right, I of t into dt. Am I right? Right? I of t into dt. Just integrate this one both sides, right? Right, let this be equation 1, right? And 1 implies I can keep it like this, right? So simply I can write it, I can do this one as dq of t will be q, right? dq of t will be, oh yeah, equals I of t, right? So again, I could write it as, yeah, if the capacitance is C, right? If the capacitance is C and the voltage across the capacitor is V of t, then what will be the Q? What is the equation for the charge stored in the capacitor Q? What is the equation for the charge stored in a capacitor, in a parallel plate capacitor? You can put it in the chat as well. Q equals
CV.
yeah, C into V of t. Am I right? QC into VC of t, right? So this becomes QT, and then that can be written by this one, right? So I can write it as C into VC, right? VC, which is equal to integration of I of t dt, right? I of t dt. So simply I can say I of t dt, right? So again, just bring this one here. So I of t, the transient current, equals C into, right? This will be some function, sorry, Vc of t, right? Right, so I can bring this dt here, C into d Vc of t divided by dt, right? So the transient current through the capacitor, right, will be written as I of t equals C into d Vc of t divided by t. Clear? Vc of t divided by t. Right. Now, yeah, just bring this equation here. Right? Let this be, okay, I'll write it here. Right? So I can say my V, right? Total current V equals R into C into d dt of Vc of t, right? Vc of t plus this Vc of t. Am I right? Plus this Vc of t. Clear, right? So now we have an equation which is RC into d Vc of t over dt plus Vc of t, right? So what I can do is, yes, we can bring this one the other side. So that will be V minus Vc of t equals RC into yeah, d dt of Vc of t. Clear, right? Now again, what I can do is, yeah, dVc of t will be there, right? So bring this dt here and then RC at the bottom, right? So how we can rewrite this is dt by RC. Yes, so C equals dVc of t divided by V minus Vc of t. Clear, right? So what I have done is I just bring this one down and dt there RC at the bottom, right? So I can write this as t by RC equals, right? So what is the integration of dVt of 1 over V minus Vc of t into dVc of t, right? 1 over Vc will be log, right? Will be log. So I can write it as minus log B minus Vc of t, right? There will be a integration constant k, right? So 1 over RC will be equal to minus log B minus Vc of t plus k, right? So now we need to define the integration constant k, right? We need to define the integration constant k. Look at here, at t equals 0 seconds, right? At t equals 0 seconds. What is the current? What is I of t? When t equals 0, then what is the current through the circuit? Oh, I would say, yes. What will be the voltage across the capacitor? Right? Of course, we don't know what is I of 0, but I would say at this beginning, right, when t equals 0, the voltage across the capacitor will also be equal to 0. Am I right? So just apply these two conditions in this equation. Clear, right? So we have an equation here and we can apply the conditions at t equals 0, V of t, right? Vc of t is also equal to 0. Am I right? Just apply these two conditions here. So when t equals 0, 0 by RC becomes, yeah, 0 by RC we can directly equal 0 equals minus log of V minus Vc of t will be 0, right? 0 plus k, right? Plus k. Now, so this will be log V. Am I right? Log V, right? So I would say log V equals k. Am I right? This minus. So when we are bringing it to the other side of the equal, it will become plus. So I would say a log V equals k. Clear? Log V equals k. Or in simple words, I can write Okay, leave it like this, right? Log V equals K. So now rewrite this equation. So T by RC equals minus log V minus VC of T plus log V. Am I right? Minus log VC of T minus log V. Okay, right. So there is a minus. Just bring it into the other side. So we can write it as minus T by RC equals log V minus VC of T minus log V. Clear, right? Minus log V, right? So we can simplify this one, right? Log. So minus means that will be divided, right? So minus T by RC equals log of V minus VC of T divided by V. Clear, right? Divided by V. Right. So now this is log. So take anti-log both sides. Anti-log means, sorry, this is ln, right? Take natural log. Right? All these will be natural logarithms. Yeah. Sorry. Yeah. All these will be ln, natural logarithms. Right? So when we are taking it, yeah, sorry, even at this equation, it will be, yeah, when I am integrating it, yeah, it will be natural logarithm, right? So I did a mistake here. You guys have to be careful, right? Because I am just working out with you, right? So whenever you found I am doing a mistake, just tell me. Okay, right. So this will be natural logarithm. So take anti-log both sides. So this will be written as e to the power, right? This will be written as exponential. Am I right? So I would write it as e to the power minus t by rc equals, right? E to the power minus t by rc equals, yeah, v minus VC of T divided by V. Clear? VC of T divided by V. Right. So now what I can do is, again, I can multiply this one there, and I can take VC of T as the subject. Right. So my VC of T can be written as, of course, what I have to do is I have to multiply this with V, and then, yeah, that will go to the other side. This will come to the other side. So VC of T will be V minus V into e to the power T by RC. Am I right? So I can write it as V minus V into e to the power minus T by RC. Again, I can take V as common, right? So I can write my VC of T equals V into 1 minus e to the power minus T by RC. Clear, right? So this is the equation for the voltage developed across the capacitor at a time t, right? So which means you are connecting the voltage, sorry, capacitor to the circuit without any charges, right? You should ground both sides. So VC of T, the initial voltage across the capacitor is 0, and then that is connected to a battery, which is a DC voltage source with a switch. While you are turning it on, there will be a huge initial current. But at the beginning, or at t equals 0, the voltage across the capacitor is 0, right? If that is given, then this is the equation to estimate the voltage across the capacitor after time t, right? After time interval of t, right? Now, yes, so that see here, that depends on both R and C, right? And also the initial voltage V, what you are connecting, right? So even the capacitor, the voltage across or the voltage developed across the capacitor depends on the exponential value of t, right? But we know that the steady state current through the capacitor is 0. Am I right? Whenever a DC voltage is connected, the steady state steady state current will be 0, right? What is the voltage across the capacitor at steady state? Now, can you using the equation? So at steady state means we can consider t equals infinity, right? So at t equals infinity, what will happen? What will be the voltage across the capacitor? Vc of infinity. What will be Vc of infinity? What is e to the power minus infinity by Rc? So infinity by Rc will be automatically infinity. So what will be what is e to the power minus infinity? What is e to the power minus infinity? Guys, someone of you have to open your mouth, right? What is e to the power infinity?
0.
Yeah, why? E to the power minus infinity means 1 over e to the power infinity, right? E to the power infinity means 1 over e to the power minus infinity means 1 over e to the power infinity, and e to the power infinity will be infinity, and 1 over infinity will be 0, right? So Vc of infinity equals 1 minus whatever the value of t and R and C, because at infinity this will be 0. So 1 minus 0 will be 1, and that is equal to the supply voltage V, right? Look at here. So now you have given a plus V here. If the same voltage is developed across the capacitor, then what will be the net current? What will be the net current? Here V, here you have minus V. So what will be the net current? Hello? What will be I of infinity? Can you understand what I am saying? Right? Of course, you have calculated Vc of infinity equals V. Then what will be your I of infinity? I of infinity will be 0, right? So V minus V. So these two will be equal and opposite. So there will be no current, right? At steady state, through a capacitor, no DC current will flow. But when t is a small value, very small value of t, there will be a transient current which obeys this equation, right? Which obeys this equation, e to the power minus t by Rc, right? Okay, we'll see about the time constant as well, right? We'll see about the time constant, right? So now, okay, shall we draw the equation for this one? Shall we draw the graph of this equation, right? Vt of t equals v into 1 minus. So let me draw the graph, right? t, right? And this one will be VC of t, right? VC of t, right? At t equals 0, right? This will be 1, and then voltage will be 0. VC of t will be 0. At t equals infinity, the voltage will be approaching V, right? Am I right? Right, so at initial, that is 0. At t equals 0, this will be infinity. Approaching infinity, there will be no poles or peaks and valleys in the middle. I would write or draw this one as this one. Clear, right? So I could write this equation of this line, right? Vc of t equals V into 1 minus e to the power minus t by RC, minus t by RC. Right, if V is going like this, then the current will be in the opposite way. Am I right? The current will be approaching 0. Right, so the current will be approaching 0, but in the opposite way, right? So this will be approaching V, and this will be I of t across the capacitor. Clear, right? Now consider, right? So we have a value, we would say a time constant, right? We have a variable called, right? So t equals, so we have a variable called tau, right? Tau equals RC, right? This is called as time constant. Right, so at t equals tau, at t equals tau, right? What will be my VC of t? Right, so V into 1 minus e to the power minus RC by RC. Am I right? What is minus RC by RC? E to the power minus 1, or I would write it as V into 1 minus 1 over E. Right? E into 1 minus 1 over E. Right? So at t equals tau, the voltage across the capacitor will be V minus 1 over E times, right? What is 1 over E? What is the value of E? Do we have calculators? Yeah, 367, right? 0.367. 1 over E is, right? So this will be V into 1 minus 0.367. So if I 1 minus 0.367, yeah, 632, 0.632 V. Right, so if you write it somewhere here, 0.632 V, right, this will be your tau. This will be your tau, which is equal to RC. Clear, right? So it will be actually 0, right? It will be reaching V, and the current will be reaching 0. So at steady state, the voltage across the capacitor will be V, and the current through the capacitor will be 0. Okay, right. So if you have any doubts, please ask me now. Hello. Any questions? Please ask me now. No questions? Right, so I assume that you guys are clear, right? You guys have understood everything. Okay, right. Now, yes, consider this circuit, right? Okay, I'll draw it again. Yes, okay, okay. Right, so I have a battery here, and then I have a capacitor with capacitance C. Then I have a resistor R, C, and battery with EMF of E. And this is a two-way switch, right? This is a two-way switch, right? So now what I'm going to do is, first, I'm going to connect this capacitor, right, to the battery. I'm going to connect the capacitor to the battery, right? And then I'm making sure that the capacitor is fully charged, right? The capacitor is fully charged, right? So the V will be transferred here, right? In simple words, I would say charged fully. When I am charging it, this will be charged, and then I am connecting it to the other side, R. So now the whole circuit will be removed, right? Once I connected to the R, right? Right, the whole section will be removed from the scene, right? So now you have a capacitor which is charged, and then that will be discharged through a resistor R. Am I right? This capacitor is fully charged, and then that will be discharged. Oh, sorry. Yeah, when this is plus, and when I'm connecting here, the current will be in the opposite direction, right? I would say, yeah, this is okay. I'll for the simplification, I am putting something like this, right? So that will be from plus to minus. Okay, sorry, this is correct, right? So it will be discharged from plus to minus. Clear, right? Now let's see again. At time t equals t, the voltage across the capacitor will be Vc of t, right? And then the current will be I of t. Current through the circuit will be I of t, right? The capacitor voltage across the capacitor will be Vc of t, and the current will be I of t, right? So there are no other voltage sources, only the capacitor. Am I right? Only the capacitor. So I can write it as R into I of t, which is C into dV of t by dt. Am I right? Right. So I can okay, equals minus of Vc of t. Right? Because yeah, it is discharging. Hence the sign will be minus, right? Again, I of t equals, from the early equations, I of t equals, yeah, t dt of v of t, right? So sorry, c into, so r c into d dt of v c of t. Am I right? Equals minus Vc of t. Clear, right? Now what I can do is, of course, I can integrate it both sides, or I can simply say yes, so dvt can go there, or that vct. Okay, I'll bring this one, right? So what I can do is I can bring this dt there, rc down, right? So dt by rc equals, right, dvc of t divided by, okay, there should be a minus, dvc of t divided by vc of t, right? dvc of t divided by vc of t. Am I right? So again, just integrate it both sides. So this becomes t by rc, right? Minus t by rc. I can write it as t vc of t divided by vc of t. Right now, just in the, yeah, will be equal to yes, what will be this one? Yes, so minus t by rc equals, what is this one? dv of t by vt, dx by x, right? So it will be natural log ln of vc of t, right, plus an integration constant k, right? And integration constant k, of course, yeah, there will be a minus, so both minuses will get, oh sorry, yeah, the minus will be there, right? This will be simply, yeah, there is no minuses in front of it, right? So it will be directly minus t by rc equals ln vc of t and plus integration constant k. Similarly, at t equals 0, right? At t equals 0, the voltage across the capacitor equals 0. As we did earlier, k will be natural log of v, right? K will be, yes, oh sorry, minus natural log of v, right? Yes, minus natural log of v, right? So substitute here, you can write the equation as minus t by rc equals ln of vc of t minus log v, ln v, right? Natural logarithm of v, right? Again, I can divide this one, so minus t by rc equals ln of vc of t divided by v. Clear, right? So if I take exponential both sides, or anti-log both sides, right, I can write this one as e to the power minus t by rc equals v of vc of t divided by v. Would say vc of t, right, the voltage developed across the capacitor is equal to v into e to the power minus t by rc, right, minus t by rc. Right now at steady state, now consider, now at steady state e to the power minus infinity becomes 0, right? So at steady state the capacitor will lose all its charges through the resistance and the plates will be neutralized. So at steady state vc of t will be 0, right? vc of t will be 0 if I draw the curve, right? Will be v across time t. This will be capital V and it will be approaching 0 with the equation B into e to the power minus t by RC. Right, so whenever you fully charge the capacitor and you are discharging it across a resistor, the transient current will be V into, which means the initial voltage V into e to the power minus t by RC. Again, time constant t equals RC. So at t equals tau, you can find out the current as well, right? You can find out the current as well. So when you are your voltage is reaching 0, then the current will also reaching 0 at this point, right? The current will be also reaching 0 since the voltage across the capacitor becomes 0. So the current will also follow the same pattern and not like in your earliest one. Clear? Right. So if you have any questions in these two, please ask me now. In our next class, we'll see the same thing for inductors. Right? We'll do the same thing, but for inductors. If you have any doubts, please ask me now.
Excuse me, sir.
Yeah.
K is equal to plus L and V.
Sorry.
K equal to plus L and V. You put minus L and V.
Okay. Yeah. This is plus K, no? No. It will be, yeah. That's a good question, but this is correct. I cannot, yeah, I'll do this again. Of course, I thought you guys can pick it up. Okay, so the equation is minus T by RC into ln VC of T plus K. Am I right? Sorry, minus T by RC. So at T equals 0, right? At T equals 0. Now tell me what is the voltage across the capacitor? At T equals 0, what is the voltage across the capacitor? Hello? See, you are fully charging the capacitor, am I right? You are fully charging the capacitor and you are just turning the switch there and then the time starts, the clock starts, right? At the beginning, at T equals 0, what is the voltage across the capacitor?
V.
Yes, but in this case, what is the voltage across the capacitor at initial stage?
0.
Yeah. So now you can do that one, right? So that is the difference. Right? So the T equals 0. I would say VC of T or VC of 0 is also equal to V. Clear? Right now, substitute the equation. 0 equals ln V plus K. So what is my K? What will be my K? Minus ln V. Clear? Yes, you are right. So are you okay now? Is it clear?
Yes, sir.
Right. Thank you. And if you have any other questions, that is the difference, right? So here we are talking about charging and here we are talking about discharging. Okay. Right. Any other questions? If you have no questions, we can wind up the session, and in the next class, we can see about the same thing, right? The transient through the inductor. And then we have one more class to study the transient in LCR circuits, right? LC circuits and LCR circuits. And with that, all the chapter will be over, right? And we can do a tutorial. Okay. Right. If you have no questions, if you have no more questions, we can wind up the session. Okay. No questions? Please talk to me, right? Don't worry about it. Okay, so we can wind up today's session, and if you have any question, just send me message in WhatsApp also, right? All of you are in WhatsApp group as well, no? Right, so you can send me your questions in WhatsApp as well. Okay, right, so now you can leave. Thank you.
Thank you, sir.